In exercise 3.2, we are given a part of a life table and we have to calculate some probabilities of life or death or deferred probabilities. And we have to do that using two different assumptions. One is using the UDD, the uniform distribution of death, and one is assuming a constant force of mortality. So before we go into the calculations, let us derive what we will need in the calculations and we'll use it later. So what can we derive assuming the UDD, the uniform distribution of deaths? I'll write it up here, and that's the following. So if we assume that the deaths are uniform distributed, then by equation 3.8 in the book, we have that the number of people in the population at time x plus s equals the number of people that were alive at x minus those that have died in this time period. And since, so this is given, and then since equation 3.4 says that dx is the difference of, so the people at Lx minus those at one time period later, we can rewrite this probability, or this first equation, by Lx plus s being equal to 1 minus s times Lx plus s times Lx plus 1. So just by substituting this dx in the first formula, we get this equation. And we will use this in combination. With the following, which is that the probability of a life-aged x surviving up to time x plus t, so for t more years, this equals the number of people alive at Lx plus t divided by the number of people alive at Lx. So this is equation 3.1 in the book. Okay, so this is one of the consequences. This is one of the consequences of the assumption of uniform distribution of death. Now, assuming a constant force of mortality, we get the following, which is the second point we need. And this means that, the most important thing that we will need is that suppose you are life-aged x, x plus t, and you want to live s more years, well then this equals px to the power of s. This is on page 48. It is derived there, and we will not go into the details here. But this is something we will need throughout, and this holds for all. So this is for all s bigger than 0, and s plus t, and t being also smaller than 1. So t cannot be a large number here. It has to be, the x plus t has to be smaller than 1 here. In any case, we are now ready to calculate some of these probabilities, starting with A. So in A, we have that we have to compute this probability, the probability that somebody aged 52.4 years survives for 0.2 more years. Now we know by definition that this is equal to the probability of 1 minus the survival, so that's B, of 2.4. Now we will use 1, the I mean, where we say this probability can be written as this fraction. So this is L of 52.4 plus 0.2, that's 52.6, and then divided by L 52.4, right? And again using I, this gives that it equals, let's do it slightly differently here. So instead of writing it as such, we will write the fractional part, so we can use this formula more easily. And to do that, we will do the following. So I'll write it as as follows. So I'll write it as 52 plus 0.6. And the bottom one will be 52 plus 0.4. And now it will become clear because s is in this case some integer, some value between 0 and 1, and x is the integer part. So x is 52 in this case, and s can be 0.6 or 0.4. So if we look at the top part for now, then we have that this equals 1 minus s, so that's 0.4 times lx, and that's 52. And then plus s, which is 0.6, and then times L52, and divide this by 52, it should be plus 1, right? Lx plus 1. And then the bottom we get 1 minus s, and s is in this case 0.4, so we get 0.6, gets 1 minus, and then this is 52, and then the other way around, so this is 0.4, L52 plus 1. Right? And now if we look at L52 in the life table here, and L53, and plug in the numbers, you should get 0.01917. So I will skip those details here because it's just a matter of plugging in and putting it in your calculator. Now this is the way to do it using the UDD, Uniform Distribution of Death. And if we compute it in part B, using the constant force of mortality, we should have the same answer, right? Because it's the same probability we're computing. So again, we start with 0.2 Q 52.4. We rewrite this in the same way, using the it's equal to 1 minus the probability of survival. And then we use the second property we derived. So this is that this becomes, instead of 0.2p 52.4, it simply becomes, let's see, becomes 0.p52. So the fractional part is eliminated, right? We see that here. So it's not x plus t anymore, so it's not 52.0.4, but just 52. And then this is raised to the power of s, which is in this case 0.2. All right, and then we use equation 3.1 to rewrite this p52. So that's lx, oh, not x, x is in this case. X is in this case 52, so Lx plus 1 is 53. L53 divided by L52 to the power 0.2. And again, you can plug in the numbers from the life table, the ones in green above, and this will give you the same answer. It should give you 0.001917. Right, so we see that this is indeed the same number. And we will do a similar thing for questions C and D. So let me remove this now. This part. In question C, we have to compute a survival probability using the UDD, Uniform Distribution of Death. So we have to compute that somebody aged 52.4 survives for 5.7 more years. Now, to use the UDD, what do? Well, we can rewrite this probability immediately as a fraction of the number of people surviving. So we have to, in the top we get 52.4 plus 5.7, which is 58.1, and here we get 52.4. And now we simply use I, the first property, which gives us that. Okay, and the top we get s being equal to 0.1. So we get 1 minus s is 0.9 times L58, because x is 58 in this case. And then plus 0.1 times L59. 0.1 times L59. And now, what do we get in the bottom? We have L52.4, so s is equal to 0.4. So here we get 1 minus s being equal to 0.6 times L52 plus 0.4 times L53. Now if you plug in the numbers again from the life table using L59, L58, L53 and 52, you will get the probability of 0.935422. So that's part C using the UDD. And we have to compute the same probability using this constant force of mortality. Now, note that we want to use the second property, but the problem is that we cannot use this immediately because we have to look at a time period of 5.7 years. So we are aged 52.4 and we have to survive for 5.7 years. But 5.7, it does not satisfy this restraint here on the right. So this s and s plus t has to be smaller than 1. And in our case, well, we have that it's equal to 5.7, which is of course bigger than 1. Therefore, we have to break down this probability, this survival probability, into a product of multiple probabilities, such that we can use this second property. Now, to use that, we will look at we will start from age 52.4, and we will look at the first part where we will reach an integer age, which is close to 53. And for that, we will need to survive 0.6 years. Okay, now we are aged 53. How many more years do we need to live? Well, let's compute that actually. We know that if we start from 52.4 and we want to live for 5.7 more years, we have to survive 5.7 more years, then we will reach the age of 58.1. So if we are age 53, we will have to live at least 5 more full years. But then we're not there yet because we need to live 0.1 years. There's 0.1 years left. So we are aged 58 and we need to live 0.1 more. And to check this, if this is correct, we need to know, you can see that if you add these time periods, that they sum up to 5.7. So we did everything correctly math-wise. Now we are ready to use property 2. Because in this case, the s and t will be smaller than 1. So in the first case, we get that this is equal to, it's equal to px, which is p52 to the power 0.6. And then times, well, this one just remains the same because we do not have an integer or a fractional age. And this one becomes p58 to the power 0.1. And this becomes, let's see, so then we can, what do we need to do? We need to rewrite this using anything we know, because we can rewrite these survival probabilities in terms of these fractions as we did before. So we do that now, and we get L58 divided by L53 here times L59 divided by L58 to the power of 0.1. So again, if you plug in the numbers from the life table, you will get the exact same survival probability. So the crucial part here is to rewrite this survival probability as a product of multiple survival probabilities. All right, let's go to the last two exercises. So let's remove this and this thing maybe. And for the last exercises, we need to compute a deferred probability. So in the first part, we need to use the UDD. So what do we need to compute? We need to compute a deferred probability of death of somebody aged 52.4. The person has to survive for at least 3.2 years and then has to die in the subsequent 2.5 years. Now, since we are using this life table with the LX, and we know of the very, let's say, important relation here between the survival probabilities and this LX, it makes sense to rewrite this deferred probability of death in terms of survival probabilities. Now on page 27 of the book, we know that we can rewrite this in terms of survival probabilities as follows. So we are aged 52.4, and we have to survive to at least 3.2 more years, but we cannot survive too long, let's say, because we have to die in the subsequent 2.5 years. 3.2 plus 2.5 is 5.7. Right, so the first probability is surviving to 52.4 plus 3.2 years, and then the next one is that we cannot live longer than the subsequent 2.5 years, so we have to add it onto that. And now we simply use part 1 of the property 1, and this gives us that, well, we can rewrite this as follows. This, for the first one, it's L55.6 and divided by L52.4. And the second one is let's see, 52.4 plus 5.7 gives us L58.1. We saw that before. Yes. And right, and now we again use I to rewrite this as using this property that we have been using all along. So let's do that. As in this case, in the first case is 0.6, so we get 1 minus s 0.4 times L55 plus 0.6 times L56 divided by, so we can write this actually as 1 because they have the same denominator. And in the bottom we get, let's see, 0.6 times L52 plus 0.4 times L53. It can be very confusing, so be very careful. And then we do minus the L58.1, and note the brackets because we get two terms now. And it becomes 0.9 times L58 plus 0.1 times L59. Alright, and then plug in everything in will give you a very small probability, which makes sense that it's small actually, of 0.030957. Alright, and now I have no room left for part F, so I will remove this part here. So for part F, so write down the answer actually. So the answer was 0.030957, and F should be the same, right? Because we have to compute the same probability using the constant force of mortality. And the question is, so how do we do that? Well, we can rewrite this, use the same way. Let's start by rewriting this in the same way into survival probabilities as we did in part E. And here we had 52.4 and we had to survive 5.7 years, right? And now you can use the product rule for the second probability, and I will show you why that is useful in a second. And it's the following. So we can rewrite this 5.7 as, okay, you have to first survive for 52.4 years and then survive 3.2 years, and then times what does it become? Well, if we survive 3.2 years, then we are aged 55.6, and we have to survive 2.5 more, right? So these numbers I'm getting through these numbers I'm getting through this, right? It's the deferred period and the time period that follows. Now, why is this useful? Well, we can factor out this probability, and doing that, well, now we have just two probabilities which we have computed, two survival probabilities which we have computed in part D. This is where we computed a survival probability using the constant force of mortality. So we can apply the same logic here. So doing that gives us, so we aged 52.4, we go to the nearest integer age, which is 53, so then we are age 53, and then we have to live to, well, 55, if you do the math. And then what is left, so we are left with 0.6, and we are aged 55 here, right? And we can do the same thing here, so we are aged, we start in age 55.6, add 0.4 to reach the first integer age. Once we are 54, we need to age for 3 more years. Sorry, 56 we have to age 2 more years. So we're 56, we have to age 2 more years. And then what is left? Well, 0.1 from age 58. Alright, and then we use part, so actually this is part D, right? And then finally we can use the second property to rewrite some of these probabilities. So this is 52, p52 to the power 0.6. This one remains the same. And then this one becomes p55 to the power 0.6 times 1 minus p55 to the power 0.4 times, this one remains the same, and this one is p58 to the power 0.1. And then, okay, so there's one more step, but I will skip it, which requires us using this one. So rewrite all the survival probabilities, all 6, using this formula, and then plug in the numbers for the LX. But this will give you, and I promise that, it will give you the same answer as in E, which is this very small probability. And note that this makes sense, right? So if you get a very large probability, it's you probably did something wrong. So why should this be a small probability? Well, this concerns somebody aged 52.4, and you are asking whether, so he has to survive, okay, 3.2 more years, so let's say he reaches about age 56, and then you're asking how long, what is the probability of death in a time period of only 2.5 years. So naturally, there's not that many people that die within, let's say, ages roughly 56 and 58 and a half. So that should be a small probability, which should give you a small number. So that just serves as a sanity check, perhaps. And this is the same for all the other answers, of course.